we define an exponential function as a function in which the exponent is a variable. So when we have a variable exponent, we know we have an exponential function, and that function is equal to a to the x, where a is bigger than 0. Our base has to be bigger than 0 to be defined, and x is not equal to, or actually n is not equal to 1. Okay? A has to be bigger than 0, and it can't be 1. So it can be a fraction, a positive fraction. It can be an integer. And some examples of an exponential function are f of x equals 3 to the x, or 1/2 to the x, or 8/10 to the x. Okay? I've seen these before. And this is what they look like. So when we graph this exponential function, what's the domain? Negative infinity to positive infinity, exactly. Because I see all values of x represented there. Okay? What about the range? Greater than 0, can it be equal to 0? Not quite, right? Because it's going to get really, 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 as this power is really, really big, negative, right? It's going to make it a really, really tiny fraction, but it will never quite reach 0. Okay? So this one will be from 0, not including 0, to positive infinity. Asymptotic to the x-axis, like our rational functions we saw. Okay? Or is it increasing? Everywhere, right? Always increasing. How about decreasing? Not at all, right? This one is not decreasing whatsoever. Empty set, not happening. And what's the y-intercept? 1, or the 0.01. Okay? Questions about this so far? All right, so that is just the basic y equals a to the x. So what happens if we make that x negative? It flips in which direction? Yeah, across the y-axis. So it reflected it across the y-axis. So what's our domain now? Yeah, negative infinity to positive infinity. It didn't change, did it? How about our range? Did it change? Nope, had to be bigger than 0. Or is it increasing? It's not. Or is it decreasing? Everywhere, right? And what's the y-intercept? 1 again. Okay? Now, let's look at this and see what happens. Let's plug in some numbers. So here is an exponential function. Y equals 2 to the x. When I plug in -2, what's my y going to be? Good. A lot of times students will say 4. Okay, because 2 squared is 4, right? Why is it not 4? It has a negative exponent. So what does the negative exponent make it do? 1 over. Okay? Had we plotted the 4, it would be up, and it would have looked funny. It looked different. Okay, so what is y equals 2 to the x when x is -1? 1/2. Okay? And when it's 0? 2 to the 0 is 1, right? Anything to the 0 power is 1. Okay? It's basically how many times is that number being multiplied by itself with 1. Or how many times do you take 1 times that number? Okay, that number to a power. And so when it's 2 to the first, 2, 2 squared, and 2 cubed, 8. Okay, so that looks right. Okay, so we have to be careful when we see this negative exponent to remember that something that has a negative exponent, we don't like to have negative exponents, so we drop them to the denominator and give it a positive exponent. Okay, so far so good? All right, next slide. The one-to-one property. We'll see it a couple times this chapter. But it says that for any a bigger than 0, not equal to 1, a to the x equals a to the y, if and only if x equals y. The way I like to say it is, if you have like bases, then the powers have to be equal. Make them like bases, then you can set your exponents equal to each other. So 16 equals 2 to the x plus 2. What's the common base here? 2. So 16 is 2 to what power? 2 to the 4th. So let's rewrite it as 2 to the 4th. And that's equal to 2 to the x plus 2. Now that we have the bases equal, the powers have to be equal. So 4 equals x plus 2. And we bring the 2 to the other side. What's x? Positive 2. Make sense? Okay. What would our common base be here? 3. So what is the power of 3 right now? Negative x, right? It's in the basement, so it's a negative 1 if we bring it to the top. So we'll have a 3 to the negative x. And 81 is 3 to what power? 4th power. Like bases, since the bases are the same, the powers have to be the same. So if negative x equals 4, what's x? Exactly. Okay? Because 1/3 to the negative 4 power means we're going to make it up to the top now, 3 to the 4th power. Make sense? Okay, good. Next one. Families of graphs. When we had an, I forgot my squared here. Okay. Doesn't matter what it is, right? Doesn't have to be squared like quadratic, but we often see it with quadratic. A times the quantity x minus h squared plus k. Your a was your amplitude. Your h is your horizontal movement. And your k is your vertical movement. Okay? Intentionally misspelled it. Okay? So when we graph a parabola or a rational function or anything for that matter, absolute value, right? All those things we've been graphing, they all follow that pattern. So my initial function is y equals x squared, or f of x equals x squared. What's this going to do if we subtract 3 within the parentheses? Move it to the right 3, okay? Which is what we expect. If we subtract 5 from it, what happens? Down 5. This thing caused problems for me earlier too. Go away. Okay, which is what we expected. 3 times it, stretches it, So now let's look at our other parent function, 2 to the x now. It could be 3 to the x or 0.5 to the x or anything for that matter, right? So I guess if I look at it from my other side. Okay, so there is our exponential function. What's going to happen if we do a minus 3 with the x? Right 3. Okay. What happens if we do a minus 5? Down 5, right? Okay. All those things. So any points that you have, we just translate them 5 units down. Okay. What about negative x? Reflection, right? But this time it's not across the x-axis, right? We have to remember this one's going to be across the y-axis. Okay. And if we have a negative x, excuse me, minus 4. Exactly. Reflection and down 4. Thank you. Okay. Make sense? All right. So Euler's number, Napier's constant, was a number that you were first exposed to last year in Algebra 2. Probably the second special number that you knew that was an irrational number, one that never terminates, never repeats, that has its own special symbol, which is the letter E. Much like pi has its own special symbol. And E is approximately equal to 2.718281. E is the base in the natural log, and we call natural log, or we write natural log as the letters ln. If we're working with a regular log, the common log, then that's a log base 10. A natural log is a log base E, which is approximately equal to the log base 2.718. Okay. Like I said, last year was probably the first time that you were exposed to it. It was in Algebra 2. Anybody remember seeing it before that? Maybe? No? Okay. So we use it when we want to, when we're a banker, for example, and we want to do things to positively influence our own bottom line. For example, when you put money into a savings account, you often get accrued, or you accrue interest on a monthly basis. When they borrow money to you or loan money to you for a car loan or for a house loan, they charge you interest every minute of the day, every second, constantly. Okay? There are many different interest formulas, but 2 of them that are very common are the compound, one that you compound n times per year, and one that you continuously compound. The first one is A equals P times the quantity 1 plus R over N, all to the NT power. And the second one is A equals P e to the RT. And you did a lot of interest formulas like this last year. So A is the amount in your account, the amount that you owe, depending on which side of the borrowing system you're on, or the loaning system that you're on. P is your principal. That's the amount of money that you loaned or are loaning or borrowing from the bank. The initial amount. N is the number of times that we're accruing interest per year. Okay. R is your rate, your interest rate as a decimal, not as a percent. and t is the number of years, time in years. If we're compounding continuously, a is still your amount at any time t. P is still your principal, your initial amount that you borrowed or loaned. R is still your rate as a decimal, not a percent. And T is still your time in years. Okay. Guys, remember these formulas? Okay. Hopefully we'll do enough problems that you'll know them off the top of your head and not need a cheat sheet. Okay. So comparison. If you loaned a bank $10,000 at 6% interest rate for 10 years, find out how much you would have in the bank if it's compounded monthly versus compounded continuously. And right now it's hard to find a 6% interest rate return because interest rates are so low. So this would have to be a heck of a deal. Okay, so $10,000, 6% interest rate, 10 years. Okay, when you see compounded monthly, you have to think about the A equals P times 1 plus R over N to the NT power. Whenever you see the word continuously, you need to think of A equals P e to the RT. So anytime they say annually, monthly, quarterly, something along those lines, this formula, continuously, the other. So we're trying to find A. What's P? 10,000. What's my rate? 0.06. Thank you for giving it to me as a decimal. What's my N? 12. 12 times a year. It's monthly. And I know N again is 12. How many years? 10. Okay. Now it's calculator math, but we have to make sure we do our order of operations correctly. Okay. It tells us to please excuse my dear Aunt Sally, right? PEMDAS. So we can't do anything with this 10,000 yet. And we can't do anything with the 1 plus because we have to divide first. So start your calculator here. Take 0.06 divided by 12. And then add 1. Okay? And then hopefully you can do this mentally, right? 120, right? So whatever you get here, you're raising to the 1/20th power. And then lastly, you're going to multiply by 10,000. Okay? So what is 0.06 divided by 12? Adding 1. And we're taking that to the 1/20th power. And it doesn't hurt to hit an equal sign every once in a while in between. And then we take that times 10,000. Everybody who used their calculator get $18,193. And how many cents? 97. Makes sense to round it to the hundreds place, right? Everybody get that? Okay. Now let's compare that to what would happen if we had borrowed $10,000 from a bank who is still charging 6% interest rate for 10 years, but we're now compounding this continuously. Okay? Won't be a significant difference, but we'll see a difference. So, same principle, right? E is our number in our calculator, so we don't even need to round it. We'll just use it as a button. And then our rate was 0.06, and our time is still 10, right? Okay. So we're going to take our 0.06 times 10, and we get 0.6, right? Okay. So we're going to take E and raise it to the 0.6 power. Mine has a, let me go to a different mode here. In scientific. Oh, not helping. May have to help me out on this one. I might have to go to my TI. Get a similar calculator to what you have. All right, so we're going to take e to the 0.6. So e is the shift of the natural log, second ln, 0.6. And then we take that number times 10,000. And we get $18,221 and 19 cents. And of course, if it had been a longer time period, 20 years, something like that, it would be more significant of a difference. All right, so feel good about those? Know how to use the formulas? Awesome. All right, next one. Last question. Population growth of a city. City planners do the same thing. They crunch the numbers. They say, okay, we've had these many residents in our town at this time, these many this year, this many this year, and so forth. Let's find a trajectory. Let's figure out what's going on so we know how to build roads and schools and have fire and policing and sewer and how to budget this stuff and how to figure out how much money we are likely to bring in. So the population of a city increases according to the model, 32,000 e to the 0.0367 t, where t is 0, stands for 1980. Okay. Graph this model and then use it to predict the population in 2008. Okay. So t is 0. Anytime you have a 0 power, that number is equal to 1. Okay. E to the 1 is, or e to the 0 is 1. 1 times 32,000 is our initial amount, right? Okay, like our principal and our p equals e, or a equals p e to the rt. So we had 32,000 people at time 0. 20, 40, 30, somewhere in here. Okay, maybe a little bit high. All right, time t equals 1. We plug 1 in. Now it's calculator work, right? Would you like to see a shortcut? Okay, let me show you if I can get this to move. Oh, I have my marker. So it wants to mark on me. Now let's move it. Okay. If we say y equals 32,000, e to the 0.0367 times x, right? We're going to get a graph. And that graph is so far outside of everything that we can't possibly see it, right? Because we started up at 32,000. And I'm not so concerned about the graph as much as the table. If I go to second table, guess what the calculator just did? All those numbers. Okay. So when we're here, 1 now has 33,196, right? That's a whole lot faster than having to plug that in. 33,196 is a little bit more than 32,000, right? 2, 34,400 and so, right? So we're almost at 35. At year 3, 35,000. At year 4, 37,000. At year 5, 38,000. At year 6, almost 40,000. Okay? We kind of see where we're going with this. Okay? So is it better to not have to worry about plugging these numbers in over and over and over again? Absolutely. If you are having to plug them in because you don't have a graphing calculator and can't go to that table, you can always just do a few. You don't have to do every single point, right? You can do every fifth and get an idea of what it's going to look like. So at year 10, we're at 46,000. Oh, and I was doing this too close. I have 10 here. Okay, so year 10 is 46,000. 45. Okay, year 5 was 38.4. So 38. Okay, so I needed to space it out anyway, right? You can change your step in the table too. But that's going to give you kind of an idea of where this is going. Save time, I'm going to draw it in there really quick. Okay? And then, what are they wanting us to do if they tell us that they want us to find the population in 2008? This model is based on year 0 being 1980, right? So how long after 1980 is 2008? 28 years. So we know we're doing something with 28. What are we going to do with it? Yeah, plug it in for t. So we need to find out what 32,000 times e to the 0.0367 times 28 is. Okay, and if it continues on this trajectory, no major economic downturns or who knows what, floods or whatever that's going to scare people away, you can figure out how many people should be there by 2008. And the US Census Bureau does this all the time. Okay? Good? Did I confuse anybody or do you have any questions on this? All right, assignment.